Okay, howdy. My name is Richard Hay, and I am a Fightin Aggie Google engineer. I was class of '93. I was in B Company, and I have become a Google engineer. And I figured I was going to help out the leadership program over at Texas A&M by giving a little short presentation on how I got to where I am, and giving some advice on things that I learned that can, help some current cadets to follow my path, or at least, if you're interested in the tech industry, interested in Wall Street, interested in different industries, maybe just not the oil and gas industry. Well, who knows? Whatever, what it is you're interested in. Hopefully, the tips I give you would help you to achieve your ambitions. That's the goal. So essentially, let's see here. So we have so this is my presentation from Fightin Texas Aggie Cadet to Google Engineer. I have a link to it in this. I'll put a link to it in this Hangout on Air that I put on YouTube, and then you guys can also use it. So anyway, so this is so I was in the Aggie band in B Company, and now I'm in Google platforms. That was my path. So I will now move to, let's see. Okay, so one of my favorite TED Talks, and TED is basically these educational talks on YouTube, is the one that the key to success is grit. So this is a great TED Talk. I highly recommend it. And basically, what is the things that and about your Texas Aggie, as everybody's heard this. I've seen them lose. I've seen them win. I've never seen them quit. Also, I don't know if you ever heard this one. Highway 6 runs both ways. Suck it up and drive on. You can bellyache about spilled milk, or you can start fixing it. You learn by doing. Life is not always roses. Dealing with adversity. These are the kinds of things that you learn in the Corps of Cadets. And essentially, these are not in the talk. These are just things that you learn in the Corps of Cadets that actually contribute to the fact the talk says that after they checked a bunch of CEOs and people that are highly successful, they found that the number one determinant of success was that the people didn't quit. As long as they didn't quit, they ended up being successful. Another thing about the Corps is it's manufactured adversity. It's voluntary. You can always quit, right? But it is real. It is still real adversity. You have to stick it out to make it through to wear boots, right? And of course, balancing academics and extracurricular activities. So essentially, there's at least when I was there was the Corps game. Like Wayne's World, which you probably are too young to remember, but they had this whole scene with street hockey, and it was like game on, got a car, and so it was like you knew when the game was on and you knew when there was a car. It's kind of like that with the Corps, right? So essentially, we used to have a saying in the Aggie band: "What happens when it rains, fish?" I mean, freshmen. The Aggie band gets wet, sir. And that is what does happen. I mean, it's that things happen, and you got to just deal with them, deal with the adversity that comes your way. So essentially, let's look at some of the things that they say in Google engineering. And just kind of compare these things, and just this is just a Google example. So some would say a lot, engineering is a game of compromise. Hard to optimize one thing without sacrificing something somewhere else. Should we build the thing, or should we buy the thing? Is it something that we can build for less money and make it cheaper, faster, better, move more bits for less money? Or is it a product where we're going to spend 3 years developing it and get very limited return, and we're only buying 10 anyway, pay the margin? You don't know what you don't know. In other words, you dive into something. Is it going to be better than the last thing? Maybe. But it could also be worse, right? So my favorite is the WTF meetings. This is also like after there's like an outage, production outage, high stress crises. That these are great meetings. There we go. These are high stress situations, and what happens is there's a big meeting the next day going, what happened? Why did it die? How do we prevent this in the future? This is the WTF meeting. Why did it die, right? But we also have we'd have like quarterly calibration, but like biannual performance evaluations, where they basically grade your performance. Are you below expectations? Are you meeting expectations? Are you exceeding expectations? Strongly exceeding? strongly sucking. There's bonuses, compensation, promotions based on performance and merit, and then they have a big focus on work-life balance. Make sure that you're kind of not spending all your time at work, right? So some more maxims. Inverse relationship between ease of use and security. So the easier you make something to use, the less secure it is. My favorite one, the KISS principle, is keep the system simple, and it'll actually yield long-term benefits. I don't always stay true to this one. Sometimes they put academics in charge. They're interested in giving presentations at Davos. Solution too simple. Yeah, you can't give that talk. So they come up with some harebrained baloney, whack-a-mole. Hey, let's go and do anyway. So you don't always stick to that one, even though I really love that one. So then there's the Heisenberg principle, which is the act of observing a phenomena changes the phenomena. That does happen. So sometimes you're testing the thing, and the whole reason it changed is because you were poking it, and it wouldn't have changed if you didn't poke it. So it isn't really a problem because it didn't happen unless you did the thing, right? Yeah. So then the trade-offs, which I have already mentioned, in terms of engineering became compromised. So, basically, you're in the Corps of Cadets, you're in the Aggie band, you're in a division, you're in a unit, parts of the Mounted Cavalry, fish drill team, this sort of thing. You do have complexity, coordination, execution. You get that in Google too. You get that in these other major tech companies also. That there's a dance. Sometimes it's a cross-functional situation. You got hardware engineers, you got data center technicians, you got software developers, you got ops engineers, guys that are all coordinating to basically implement the solution in tandem. So the thing is you have the Google data centers that power all of the applications that Google provides for free to everyone that uses Google stuff. We do have fault-tolerant software and cheap hardware, and that makes we move more bits for less money. That's how we're able to deliver our solutions and deliver things for free that other people used to charge for, and then also put advertising in there and make it to where we can make the money, and so the users don't pay, the advertisers do. So basically we do have now, and then it's improved. So we not only have mostly fault-tolerant software, cheap, cost-efficient hardware platform, sophisticated performance tools, automated health monitoring, and we basically get free food too. So this is kind of how things are put together at the Goog. So I'm interspacing the presentation with actual pictures that we published, I believe, in 2013 of Google data center sites that are all over the world, which are just great pictures, because in the past we just really didn't share many pictures of our data centers, and I've not really honestly certain why we decided to do it in 2013, because a lot of it was secret before then. I couldn't talk about it, but once they published it in the New York Times, they let me talk about it. So that's kind of how it goes. So basically, the size Google is, building a computing infrastructure to keep it running is one of the most challenging technical areas at Google. And then building this infrastructure at a cost that can be afforded. I mean, even Google, that makes lots of money from advertising, can't just afford to spend whatever amount of money. It has to have some caps. It has to be worth it. There has to be a business case for why you build the things that you're building. And you do want to lower power consumption and drive efficiency gains, and do all those things to help basically improve the system. So we have all these different systems: web search, Gmail, ads, our file system, databases, and this all feeds into Google Plus and Google Apps, YouTube, all Gmail. Any Google service you can imagine using. Google Maps is all built on this infrastructure. They're all using the same infrastructure. So this is a picture of a data center example, and this just gives you this example. To me, it always kind of looks like the scene at the end of Indiana Jones, where the warehouse goes on and on and on forever. Data centers don't go on forever, but this is like 20, 30 rows, tens of thousands of machines in each building. that are all networked together and then connected to the outside world that are serving all of the services that we offer for free, and the billions of users that are using Google on a daily basis. So basically, it's growing, right? I mean, hey, we're trying to add the next billion people on the internet, trying to get India. Let's go, rack it up, get everybody a smartphone. Let's get everybody on the internet. Let's advertise to them. Let's monetize those users. Let's get everybody using free services and giving them value add for that, and then making it to where people that are trying to sell the stuff that can show you things you're interested in buying, and then you buy it. Boom, everybody wins. Right, and all the Google apps are more people, more usage, more data, more, just and part of this is helped by Moore's law, which Moore's law is a very famous Silicon Valley axiom, where I think it's the amount of computing, capability will double and the cost will half every 3 years. I think that's right. So you can get more processors, more storage, more memory for less money every 3 years. And this has, I think, been true since 1950 or so. And so it sticks to this gun. I mean, basically this growth, this explosive growth in the technology, I don't know that you can maintain it forever, but it's pretty good. And so essentially the cost of any individual hard drive or any individual memory module or any individual CPU pretty much is kind of approaching zero. I mean, it's like moving towards, you can do so many processors, so many cores, so much memory, so much storage, that it really does lower the costs of deploying. I mean, you still have to build these data centers. You still have to put servers in data centers. You still have to put hard drives in those servers. You still have to put memory in those server trays. You still have to put CPUs in there with multiple sockets. So you still have to build and maintain this facility. That's not a zero cost. But if you make it as efficient as possible and power it with as little power as possible, make as much of that power renewable, and then cool it efficiently, then you can basically deliver more for less and make it to where your competitors also have to deliver really high quality services to the users, because you're out there. I mean, they can't raise their prices because we exist, and that's good for you. So yeah, send in the cavalry. This is the cavalry, and that's what we do. And basically, there's been a revolution, and this is just discussing again the Moore's law stuff. Disks are getting cheaper, memory is getting cheaper, microprocessor performance is increasing. Also, the networks are improving. Basically, you're building out more better, LTE, Verizon, AT&T, Comcast, even Google Fiber. They're all improving internet connection speeds, and we're trying to also find ways to improve speeds and connect people in developing countries where they've never had internet at all. Just remember back to whenever you first discovered the internet, that first couple of weeks when you're like, "Oh my gosh, this is amazing." That's what we're doing, right? So, love this guy's mask. Solder, he's welding something. We have facilities with actual mechanical parts, and sometimes you got to basically kind of hack it. Give me the plasma cutter. Yeah, okay, it happens. Right. So if gas mileage, for example, had been improving the way microprocessors and memory and storage have been, then it would basically allow you to have 1 liter of gas taking you to the moon and back 30 times in that same period since 1980, just since 1980. Pretty crazy. So here at Google, we have a platforms organization, and it's got, there's hardware, software, manufacturing. So we build stuff, we code it, and then we ship it, and then plug it in and, rack it up. And this is the hardware, software, manufacturing components, right? And then here's just technicians in the data center working on hundreds of machines. Basically every day you get these tickets. Machine blah 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 is broken. Go fix it. Replace this RAM stick. Bad hard drive. Swap a CPU. Whatever it is, right? And then the technicians go and fix it. So yeah, so here's just a comparison of like some different symmetric multiprocessing servers and PC performance of those servers, and then how Google does our own servers is a little bit in here too. Which servers, whether I like it or not, and I'm not really crazy about it, that's the canon. A boom. That's where you're getting the boom for that's where, you know, that's where all the magic happens. That's where Gmail happens. That's where your calendar happens. That's where Gmaps happens. That's where Android happens. That's where, you know, what makes your Android phone powerful is not the phone. It's the 10,000 machines at the data center that figure out what it is you just said when you're using Google Translate, or what that Japanese guy said when you have him listen and have Google Translate tell you what he said. That's the Google data center. That's the power of those machines in the data center. So basically, we do have failures. There are failures. In the Corps of Cadets, there are failures. You know, so people, actually, a lot of life is about how you deal with failure. I think one of my favorite shirts at Google was this shirt that said grep minus V success. Now, grep is a Unix command. The minus V flag is the exception. So when you do a grep minus V success, what you're really saying is, show me everything that didn't succeed. Show me the failures, because those are the interesting things. If it succeeded, then I don't need to look at it because it's working. If it failed, I want to know about it. So basically, you have like some numbers like these mean times between failures. That's what MTBF stands for. Even with a 3-year MTBF, like even if only one thing fails every 3 years, our mean time is, you know, for one unit. Because there's so many units, you basically get 1 in 1,000 that would fail every day. Right. See, so essentially, if you think about it, like 3 years, 365 times 3, that's 1,000 days. If you have one fail a day, with a 3-year MTBF, you get one failure a day. Right. Small, like Google applications, the smallest one uses 2,000 machines. So essentially, you'd have 2 failures per day in that application at minimum. And so basically what they're saying is, don't put over dependence on any one machine in your software architecture and make any one machine like something you can't live without, because if it may be that one. If the 2 a die a day, it could be the magic box that we can't have that guy die. So anyway, yeah, but you know, replicating those functions, redundancy, capacity, you know, basically Google goes the strategy of buy a lot of cheap servers and then write software that expects them to fail and then works around it if they do. So it's better to write fault-tolerant software than to basically depend on highly reliable hardware, because that's a fool's errand. So learn from failure to achieve excellence. Of course, that's what Google. That's what the Corps of Cadets does also. I mean, basically, it's not about driving you into the ground and making you quit. It's about, you know, if at first you don't succeed, lower your expectation. No, I'm kidding. It's about picking yourself up whenever you fall down. You go on a death run, which I probably don't have anymore, but you go on where everybody yaks. You just run until everybody pukes. You keep going. You pick yourselves up. You run back to the quad. You sing the Jodies. So I also like this picture. See, this is a cool picture just because it uses the 4 primary colors. It's got all the. I think this is in Finland. You got like the red, the blue, the green, the yellow, and then the little bike, and then it's like this. This is part of our hydro plant. Google uses water to cool the servers, believe it or not, and what's called evaporative cooling. So what happens is there's cold water, or at least outside temperature water, that is piped in through the copper pipes. The hot air coming out of the servers in the back is, heats up the hot aisle up to about 130 degrees. The hot air goes into the copper cables or the copper piping that has the cooler water in it. The heat transfers into the water, heats the water. The water goes outside, and then you just, dribble it down one of those little step stair waterfalls, and then it evaporates off and the heat just dissipates into the wind. Because the whole point of this entire process is to make the heat go away. Take the heat from where it's hot, move it outside. That's the game. So, of course, Google makes these decisions on whether to build it ourselves or whether to buy it from somebody else. This is probably the coolest picture of the hot aisle I've ever seen in my career. It does not look this cool when you go to the data center. No one ever goes in there. It's super loud, by the way. There's like these, you see these fans on the sides of the servers pushing hot air into this hot aisle. And then there's the copper cable or the copper piping up here that takes the heat rises. The copper piping has the water in it, heats the water, water takes it away. And then the photographer in this case, like greenlit the whole, I mean, it's not green. She did that, right? The photographer, you know, glam it up. How do you make the hot aisle look? This is it. This is how you make the hot aisle look cool. So obviously I work on networking. So what I do personally is networking. So, you know, how do I make the networking faster? How do I reduce oversubscription ratios? How do I bring faster switches? Anyway, that's, you know, so, and then this, I have a couple of slides describing some of the problems that occur in networking. You know, so the fan-in problem is probably my favorite, because we started building networks that were non-blocking. So there was like no oversubscription between the top of the rack switch and the aggregation layer, and all the data could get out. But that didn't solve the fan-in problem, because the fan-in problem was one guy asked a question, 50 guys answer, the 50 guys kick the one guy's butt. You know, that problem gets worse whenever you make it to where everyone can send data to the network. Whenever it was congested, it was like, maybe the 50 guys don't kick your butt as bad because they can't get to you, because they can't even get out of their own switch. Now they can. They totally kick your butt. Another really cool picture of our water cooling piping infrastructure, which is probably in a different data center. But again, part of the same thing. Hot air rises, heats the copper piping, heats the water, water takes it away. And some just efficiency diagrams on how that works. We do have raised flooring, so you use these little suckers to kind of like open up, you know, bring the raised floor out and then kind of get under there, and there's pipes and other kind of cabling down there below the raised flooring. Okay, good story. This is a good little, this is an Aggie core tie-in. So true story, this actually happened. We have a lab in the old Silicon Graphics manufacturing warehouse in Mountain View, and there was a test bed set up in the lab called CT. I did not name CT. CT was named CT before I came in. So they basically, we said, oh, we want to build another test bed to test. There was an interconnection fabric that needed to be tested, and so you had to have one cluster on this side and one cluster on that side to basically run traffic through this interconnecting fabric. And so we needed a second cluster. So I asked for the name BQ specifically because I found out that no one else was using BQ. I was like, I want it. Give me BQ. So the cluster naming allocation engineer, there is such a guy. He said, well, why would you want BQ? Just out of curiosity. And I said, well, you can't have CTs, or you can't have CT without a BQ, which he didn't get. But that's okay. I didn't really explain it to him. He gave me the name BQ. We're all good. So now in that lab, there's a CT and there's a BQ cluster. We do have technicians that we hire at the data centers that are basically, they typically work on site. So we like to select places where they have good wet bulb evaporative temperatures. That's why there's no data centers in Texas. There are some in North Carolina, Washington, or actually Oregon, Taiwan, Malaysia, Finland. Finland's a good one. And then also the Netherlands has a couple of them, and some other sites too. So that's just a few examples of places where these guys would work. So here's one for, all you people at Texas A&M right now. Just about, what do you want to major in? So let me just talk about technical majors versus non-technical majors. I interviewed a lot of people. I've interviewed over 200 candidates for jobs at Google. And I just had an interview day before yesterday. So I still interview people a lot. So Google gets about 3 million applications per year. At least in the group I'm in, lots of Stanford PhDs. One of them, Hong Lu, she got her master's from A&M before her PhD and her PhD in physics is from Stanford. I'm claiming her. She's an Aggie since she is a total genius, and she tends to say she's a Stanford PhD, but I'm like, she's got her master's from A&M. So we do have a lot of foreign nationals that come in, and so if you may not have noticed, a lot of the schools in the United States have foreign nationals getting their graduate degrees. So Most of the graduate degrees are going to foreign nationals, not to Americans. I mean, it's a majority. It's not just A&M, it's at every school. So there's a need for more people, more Americans, to slog it out and major in hard subjects. Now, I think what happens is that in America, a lot of kids, a lot of people, they get a lot of things handed to them. That it isn't very hard, and they basically they sleepwalk through high school, they sleep through middle school. They get good grades. They don't have to try that hard. They get to college. Oh, that calculus is hard. I'm gonna switch to poli-sci. Why would I want to stick it out? Why would I want to do the hard thing? Because it's hard. My graduate advisor says I got to keep my grades up. I'm getting C's in computer science. I need to switch to something I can get A's and B's in. So now, for myself at least, and this happened to me in 1993, I went to the Career Center. I don't know if you've been to the Career Center. It's very exciting. Now, the Career Center, you go there and you find out that 80% of the jobs go to 20% of the graduates. So the 20% of the graduates that have technical majors, your science majors, your biology majors, your chemistry majors, your mathematics majors, your computer science majors, your engineering majors, they get 80% of the job offers. That 80% of the companies that are looking to hire people right out of college are looking at those technical majors. And so that means that those 20% get to pick from which one of the 80% of the offers that are presented to them, which jobs they're most interested in. And it's competitive. Basically, the companies are competing to get that 20% of the graduates. And obviously, it doesn't hurt to have good grades and do well. So, I mean, yes, if you're getting C's in computer science, you might have to settle for the lesser ones of these 80% of the opportunities. But and the better you do, the more you're going to be pursued. So the other 80% of the graduates end up fighting for the remaining 20% of the opportunities, which are not as good. These are the assistant manager at Taco Bell, hey, you can take another year and major in additional education and make $25,000 to become an entry-level teacher. Basically, what you major in is as important as how well you do. So your academic advisor probably tells you, you got to get good grades, you got to get A's, you got to do your best, you got to basically do well on your tests, your GRE, and all this. Because essentially, your graduate students is giving you good advice on how to become a graduate student. That's what they know how to do. Okay, that's great if you want to become a graduate student. If you don't want to become a graduate student, maybe that's not so great. Maybe you shouldn't have put so much emphasis on getting straight A's in history. What are you going to be? You're going to be the 80% fighting for the 20%. You're not going to be the 20% getting the 80%. And basically, my advice here is just it's worth it to stick it out in CS, math, physics, engineering instead of switching to an easier major. It does pay off. That the long-term payoff is much greater for that effort. If you put the effort in, that you will see a return. So speaking of technicals, and I just had a picture of the fistula to knock it out. So here's a technical argument that I actually really had with Hong Lu, the A&M master's degree, Stanford PhD in physics. So we were testing a switching chip, and we saw 950 nanoseconds of delay, that it took a packet 950 nanoseconds to go into the chip and come back out again, which is less than a microsecond. So 950 millionths of a second, that's how long it took to go in and out of the device, which I thought the developers would be super happy with. Instead, they said, what? The vendor said it would be 700 nanoseconds, which is less than 950. And so I thought 950 was pretty good, but okay, you're going to bellyache and say you wanted 700, then why? So I was like, well, why is it more than what they said it would be? So I talked to Hong, and she said, well, how long were the cables? And I said, well, the LC fibers were about 20 meters, and then I had a little coupler. There was a little converter that went from LC to light peak, and then about 25 meters in, about 25 meters out. So she said, well, there you go. I said, okay, you're going to be more specific. She said, well, the latency of the speed of light in a fiber, she said, is 5 nanoseconds per meter. So every meter, you incur 5 nanoseconds of delay. So since I had 25 meters in, 25 meters out, I had 50 meters worth of cable. She was saying that at 5 nanoseconds per meter, that 50 meters translated into 250 nanoseconds, which was exactly the amount of delay above the 700 promised that I was observing. So that, in fact, we were seeing 700 nanoseconds of switching chip delay, and we were seeing 250 nanoseconds of cable delay. Well, then I divided the speed of light, 299,792,458 meters per second by 1, and I got 3.3 nanoseconds. I got 3.3 billionths. So I said, hey, I did the math, and it's not 5 nanoseconds per meter, it's 3.3 nanoseconds per meter. So it doesn't account for all 250 nanoseconds of delay. So I said the 50 nanoseconds was only responsible for 170 nanoseconds or so, not the full 250 nanosecond delta. At which point, and this is another cool data center picture, Hong responded that that is the speed of light in a vacuum. But the speed of light in a silica fiber is 5 nanoseconds per meter. So I learned something from this little argument that I lost. Don't argue with an engineer with a Stanford PhD in physics when discussing the speed of light. And, 5 nanoseconds per meter and 50 meters of cable does account for 250 nanoseconds latency, which is the difference between 700 nanoseconds and the vendor suggested, and the 950 nanoseconds observed. So the next week, and this is true, week right after this, it was reported from Europe that the scientists at the Large Hadron Collider, the LHC, had inaccurately reported neutrinos exceeded the speed of light because they forgot to account for the latency delay of the speed of light in the silica fiber. I'm like, oh, I know that one. Just did that with Hong. Anyway, so good times. Yeah. So we do have an Oklahoma data center in Pryor, Oklahoma. It's on 900 acres of land. We only use 20 acres. So the funny thing is, Oklahoma allows you more. You can buy more power if you own more land, and we want to buy a lot of power. And then we raise cows on most of it so that we can get the agricultural exemption. This is not Oklahoma. This is a picture of the Finland data center, which was an old paper mill that we converted into a data center. So this is some more information, some more Google stuff. Probably should trim this down. So and basically, I put in a little puzzle, like basically an example of one of the situations where something starts happening. You're like, well, what's going on? You're looking at symptoms. Why is it doing this? That's weird. In this case, it was basically a bunch of machines saw a slow drive. It always seemed to happen in a particular drive slot. Swap drives sometimes have the problem, sometimes not. So that was an example, and you can go back and look at it from the link of like an example of a real data center problem. This is a picture, beautiful picture of our Oregon data center on the Columbia River in the Dalles, Oregon. This cute little building over here is they actually have some apartments in here. So whenever I go up there, I like to get the apartments and say, hey, I'm just going to stay like 100 yards away from the data center building. Now there's actually a space in the middle. They're actually going to build a third building. 2 stories that'll have just as much capacity as the other 2 buildings combined, because we ran out of power. We consumed all the power we made the 30-year deal for in these building 1 and building 3. We didn't have enough power to build building 2, and then Oregon came back and said, well, we'll keep selling you the power at the same rate and just double the amount of power you can buy from these hydroelectric plants, and so we will do that and build the extra capacity, right? Because essentially power at these data centers in Oregon is 10 cents on the dollar if you built them in California. So Erin Brockovich was a great person, but she also raised the power prices in California to the point where there's no way anyone builds data centers here. Okay. Right. So essentially, this was like more description about the issue where it turned out to be the power cable was fuzzing out the magnetometer on the drives. And making it to where it would move the drive head, cause a disk read error. And you saw a number of these disk read errors that exceeded the 16-bit counter. So it assumed that there was only ever going to happen 16 bits, which I believe is 65,535 times in the life of the drive. Since it was happening all the time, it was basically flipping that to more than 65,000 on every system that was encountering it. And then the next register over was how old is the drive, and when you flip the high order bit of that, it said it was 10 years old. So it would inaccurately report its age because there were so many of these disk read errors. The raised flooring again, rows of machines. So actually, here's a good picture of what Google looked like in 1997. I don't know if you were alive in 1997, probably 5 years old, something like that. I had been out of A&M for about 4 years at this point, but basically it was just a bunch of old machines that were in the Stanford lab and that they were putting it together to run Google at google.stanford.edu. At that time, it was codenamed Backrub. That was the name for Google at that time. Also, whenever Google first started building racks in the, I believe it was the Equinix or whatever, there was a data center here in San Jose, and we were co-locating there with Yahoo and other, Amazon and other companies. And basically, this is what the Google, they were charging us by how much space we took up with it, not how much power we were drawing. So we tried to stuff as much crap into each rack as we could. Right. So that was interesting. This is a data center in 2001 that has yet to be filled up. And then here's how we basically fill it up. And basically, yeah, so we go through, we do design these platforms. We design it with Google specific. So when you design the whole data center, servers, racks, cooling, networking, everything, you can optimize for things that make it tough if you're basically just making one of those individual components and cut costs. So yeah, it's Google's a big company. It's building powerful, innovative computing. Got a lot of smart people. Efficiency matters. And, basically, Aggie's, we know about protecting valuable assets. We know how to, look at Ryan Crater, who, by the way, cannot believe he didn't run for junior yell leader. It would have been a shoo-in. Oh, well, I guess he didn't want to be yell leader. But he did a great job blocking that SMU wide receiver away from hitting up Rev 8 before she retired. So I got some links here to, Google data centers, Google server information. Interesting. So all your data, all the people's data that lives on disks, whenever we're erasing the disks, we do actually try to erase them and resell them to other companies so we can resell them on the aftermarket. But we write over the disk like 50 times with zeros and ones to make sure that no data could ever be recovered off the disk. If the 50-time overwrite fails, then we literally physically crush the disks. We put like a steel divot through the disk platter and we destroy it. And this is a picture of that. So yeah, it's fun. My personal job is to break things on purpose and complain about it. And so, even though we get a lot of people apply, you can't really get a job unless you try. Now, only a small percentage of people actually get chosen, but you basically look at the job openings, go to google.com, job students, look for things out there. If you're majoring in industrial design, if you're majoring in it's not just software development, it's not just computer science and computer engineering. It's there's electrical engineering, chemical engineering, mechanical engineering. There's jobs for machinists. We have openings, things that we need to get done for all those kinds of jobs. Look on there, see something you like, and take a shot. So yeah, I can't get hired unless you try. Good luck, and if you do actually find a position that you think you're qualified to apply for, just go ahead and ping me, rhay@google.com, and I'd be happy to recommend you for the position, give you a little leg up. See if I can get you at least a phone screen or an interview. From there, it's on you. So, yep. That's about it. And, TU only racked up 59 yards in their bowl, lost to Arkansas, which never gets old. Of course, we lost to Alabama 59-0. But if they bring up how many yards they got against Arkansas. So you guys have a good day. And I will maybe make another one of these at some point, but this is my little presentation, and hopefully you enjoyed it. Hopefully I didn't get too technical. Hopefully I didn't get too far in the weeds. I probably got a little bit in the weeds. Yeah, good luck and gig 'em.